Okay, so yes. So this is the engineer representation of a sensitivity analysis, but this is very ambitious because, you know, it's not so easy to set up the analysis so that you can do simultaneously all this kind of uncertainty propagation. But ideally, yes, ideally you should, when you say, for instance, the solution level and model structure, you are really into some kind of model averaging process. Okay, so we have it with Arnold when we do irrigation modeling, and there are several different formula for evotranspiration. At least 5 of them are very popular, so we have a trigger, and the trigger can select one of the 5 at runtime. When I say runtime, I mean simultaneously with everything else. Okay, so this is a kind of activating even epistemic, what some people like to call epistemic uncertainty, no? So uncertainty about the state of knowledge of the system, which I think, but you can just say that you need to want. And so this one is clearly the uncertainty analysis, and this one is clearly the sensitivity analysis, though you should never use a histogram because it's the pie chart, because it's not a good way of plotting data, but just for the sake of illustration. This is, well, the point we made in this paper on Nature was that the users should ask model to come with some kind of uncertainty and sensitivity analysis, no? Because otherwise the model will be a kind of a black box. I will also a bit use, who has read Nassim Taleb among you? No? This book is very nice. I suggest that you read it. Nassim Taleb is a broker, but he thinks like an engineer very often, no? Because it has a lot to do with uncertainty and risk. So for me, the problem is that there are many methods for sensitivity analysis. So which one should I use? And I think it's very important that you choose a method because it particularly fit to the problem you have. So there must be a reason for choosing a method versus another. Okay? So for many applications, you can use variant-based method, for instance, which decompose the variance of the output. But you will agree with me that if the output is long-tailed, no, very skewed, doesn't make any sense to talk about variance because the variance will be very erratic, no? Then you may be better to look at the entire distribution and use something like the so-called moment-independent methods. And so this is a book translated into Chinese and which you can download for free without spending 150 euro on Wiley because it's available here. It was pirated by the Russian, by Mariia, and it's found on LibGen, so but there is a copy also on my website. So this is a sensitivity analysis for dummy in the sense that this is to explain people how sensitivity analysis works. This is a scatter plot of the output versus the input by sorting the input with respect to two different variables, but the points are the same. No? Those are the same points plotted differently, versus x1 and versus x2. Okay, so which factor is more important?
X1.
X1. Why? Yeah, it drives the variation, and the other one doesn't seem to be driving much. So the second one seems like almost noise, okay? But then you can go one step further and say, why don't we slice the variation of the factor into bins containing roughly the same number of points, and we compute a local average, and the local average is the pink dot. Okay. So the pink, we will agree with me, if you understand this notation, that the pink point is a local average, which I write in this way: the mean of everything but xi condition on xi. You're familiar with this kind of notation. Conditional probability. Okay. Then the next step is to take the variance of this conditional probability, no? And this is a sensitivity measure of the first order, known.
So in a sense, we are taking variance of all the pink points, right?
Yeah,
Yeah.
the variance of the ping point. Exactly.
Which are
So
the averages?
this compact in a single number, what you would otherwise have to look at as a scatter plot. Yeah. And clearly, which variable has the larger variance? Okay, the upper one, xi, yes. Obvious, no? Because the other one is almost a flat line, much less variance. Okay. Okay, so this is a very old paper I did with Stefano, discussing when to use what for sensitivity analysis. And I haven't told you anything about the total effect, but maybe some of you know already what it is. Total effect is a measure of sensitivity which resembles the first order index, but which also capture the higher order interaction between factors. Okay, so you may have a factor which doesn't do anything, like x1 doesn't do anything, but coupled with x2, it does something. In this case, you say it has an interaction effect, which is non-zero. So, then maybe we can go later if you want into the estimation procedure, but and this may be an interesting part of the talk. But the first order effect is good to decide which factor needs to be determined better, if this is your objective. Where should I spend my money if I have only limited amount of money to get better measurement? The answer would be the factor with the higher first order effect. But if you have a different question, and the question is, which factor can I get rid of, or can I fix? Then you need the total effect, because you may have what I just mentioned before. You may have a factor which doesn't do anything at the first order, but is active at the second order, okay, or third, or whatever. And for those of you who listened to the talk of this morning, the more you move away from the model to incorporate more triggers, the more this interaction effect will be important. Because by definition, trigger is very nonlinear. No? It can either be there or not be there. And so this makes a difference. And there are different ways to compute sensitivity indices. These are a couple of papers. One is by me, another by Art Owen. But maybe, are you interested in a crash course on how to compute the indices? Just very quick. So, without explaining why, imagine you have a matrix x1, xn, x1 row, so x1 and x, no, it was correct, k, I, and k, and 1. Okay, so this is the n rows, and this is column 1 to n. Okay, so this is a, imagine this is a base matrix, no? Where each row is a sample for the simulation. Those are the k uncertain variable, and you sample this matrix random, or even better quasi-random, or whatever you want to use. So if you imagine that you have a second matrix which is almost identical but only different in the sense that it contains different points. Let me call it star. 1, 1, 1k. So these are two matrices which, for all intent and purposes, are done almost identically, but they are different, okay? Okay, those are two different matrices. Again, you can compute for each row one output value and so on. Now, the beauty of computing the sensitivity indices is that to compute the first order index, you need a matrix where all columns are different but one. Okay? Imagine how could I make it. Imagine you have this is identical to the one matrix above, but for one, no, should be, this is all different, no, but for one value it is the same as the matrix above. So this is a matrix which comes entirely from here, but for one column which comes from here. Are you with me? Very simple, no? So from this kind of matrix, no, from this and this, from the value of y corresponding to these two, you can compute xi, the SI, the first order sensitivity indices. If instead you have, sorry, this is star, eh? So this is a matrix which is, if you wish, quasi this, okay? Then you can have a different case where each come from almost symmetrical, each come from the first matrix. In this case, xi come from the other matrix, okay? So this is quasi this. Okay, so if this is A and this is B, this is a matrix of quasi B, this is quasi A, and by coupling those two matrices, or these two matrices, you can compute SI and STI. Okay?
And every matrix is the result of a full-blown Monte Carlo simulation.
Yeah.
So that's it. Yes. And you're kind of switching on and off some inputs to produce those.
Yes. For instance, this matrix could be quasi-random matrix. Mm-hmm. And we always sample in 0, 1. Eh? We always assume that you are capable. We don't want to hear about distribution. We don't care. We sample in 0, 1 because then we know that we can always map the 0, 1 into the actual distribution of the parameter. But this is done in another part of the program. No? But this very simple arrangement with two base matrices and k of these matrices, no? You can compute all sensitivity indices of the first order and total. So you have n simulation 2 times plus k. So this is the total number of model simulation which you need to compute first order and total sensitivity indices in this very fundamental arrangement without making tricks, let's say, no? Okay. Another way of looking at this is to say that when you compute the first order indices, you look at two different function values. Let me start from the other one. To compute the total sensitivity index, you look at two function values which only differ in one direction. Okay, so we call this one step into the xi direction. To compute the first order indices, you look at function values where you do a step in the non-xi direction. Okay, so you move in everything but xi. So with this very symmetric kind of reasoning, no, you can compute all sensitivity indices. And this is very elegant and easy to do, and you can code it for yourself if you code in whatever language. Huh? And you can redo this kind of analysis. And then there are, I didn't give you the forms of the relationship, but it's very simple. It can be a product or a subtraction. There are various estimators, by the way. There are various ways you can combine these 2f function value to get the index with different properties, no? But this is another story.
Those are the mechanics under the Sobol indices, right?
Yes.
Even your recent work, which is not, I think, yet published with Arnold and Pamphile, it already is able to compute the total indices from a single Monte Carlo sample, right?
Yeah.
So it's kind of same logic that you showed the intuition before, and much
because
a single matrix.
Yeah, because we wanted to do sensitivity analysis for dummies, no? And so what we did was to go back to this histogram, no? No, I'm going back.
Yes, somewhere there.
Okay, so this is not a good example because it's not scaling 0, 1, but imagine that this was nicely scaled into 0, 1. In this kind of plot, you would see more empty space here than there. Okay. Now, when you look when you work in Monte Carlo, something you normally do in many dimension, k dimension, is to look at the discrepancy, which is a measure of how non-homogeneously the points are spread into this k-dimensional space. So, if you wish, a hand-waving way to describe discrepancy would be the largest hole you can find in a multidimensional cube, no? So the point, or the point where the distribution is the most different from the average density. No? Imagine you have n points to play with, and you divide the hypercube into n cells. There should be 1 point per cell, no? So how many cells instead are empty? This would be a measure of discrepancy, no? And this kind of discrepancy, which is the reason why we normally use quasi-random sequences, because they have low discrepancy properties, better than pure Monte Carlo, no? We can apply to the xy plane and say, why don't we compute the discrepancy in this simple bidimensional plot and see how is the discrepancy? Because clearly, this plot, no, has more discrepancy than this plot. No? So we say, this could be a good sensitivity measure. So we tried, and we found that in this way, this kind of discrepancy, which we compute very cheaply, behaves very much like the total sensitivity index. Also because this can also capture, imagine you have, normally, so you have 0, 1, 0, 1. This is the way we do it. Imagine the point do this. No monotonic. But now you have here, no, region of empty space, no? So even if you had a non-monotonic behavior like this, the total sensitivity index would of course capture it, but also this method would capture it. So the way we do it with Arnold is to, we have set up a system whereby we dispose of some 10, 20 different mathematical functions with some 10 different distribution which we can play, and then we do a tremendous number crunching where we try total sensitivity index and this measure on all this combination of function, and we look at the brute result, no? And we say, oh, look here, you know, very often they work together. They go nicely together. So this would be a sensitivity analysis for dummy because it doesn't need calculus, because the variance is an integral. Doesn't need statistics. You don't need to explain ANOVA and the interaction. And simply does the job of identifying influential factors. Okay. Okay. Okay, let's move on. Yeah, this I just mentioned. This is, okay, we are computing. This is about software. There is a lot of software. I cannot even list now because there is so much coming out now. But this is just some of the software which are around. This is another software which we published on the Journal of Statistical Software, also to do computer sensitivity indices. A lot of this stuff goes on in R, of course, no? And then there is a model effective dimension, which is a concept which is very useful, and I want to discuss it with you a second. So, what is the effective dimension? You may have a problem, a model with many parameters, but only a very few are active. So this model has intuitively a low effective dimension. Now there are two definitions of effective dimension, ANSI 3. Here I only express two. One is how many factors is important, and this is called the truncation. And the second way to define effective dimension is in terms of which is the highest interaction terms you have to consider, second, third, or so on. So these two definitions taken together, or a combination of those known as average effective dimension, can help you understand the true complexity of your model. Okay? So it's useful to know about effective dimension because effective dimension also has a contribution to make to the build-up of uncertainty. Clearly, a model with a larger effective dimension is more likely to produce uncertainty range in the distribution. Yeah, this is a mean dimension, and this is a paper by Art Owen where you can compute the mean dimension directly from the sensitivity coefficients. Okay, it's very straightforward. So again, you know, in a sense, everything holds together. Now you compute the sensitivity indices, you already have the mean dimension. This you don't get with my approximate method. Not yet, at least. No.
And Art Owen is a brilliant mathematician and statistician in Stanford University.
Yeah.
Yes.
He's a real mathematician, unlike me. Art is really good. He's a very good guy. Okay. So the advantages of the variant-based method is that they have a graphical interpretation of terms in terms of scatter plot, a statistical interpretation in terms of variant decomposition. If you know, okay, none of you is statistician, but maybe you heard about ANOVA decomposition. Or functional decomposition. You can decompose a function into terms of increasing dimensionality. Likewise, you can increase the variance into a sum of terms of increasing dimensionality if the variables are independent. And so you can say a full variant decomposition would be based on all the first order terms, all the second order terms, which would be k times k minus 1 divided 2, and so on and so forth. One reason why we use total sensitivity indices is that we don't want to compute all these indices, okay? We only want to compute SI and STI. And to explain you once and for all what STI actually is. So the full variant decomposition for S would be S, for, I don't know, 3 variables would be this. So this would be the full functional decomposition or variant decomposition, because S is simply, S is simply the conditional variance divided by the unconditional variance, okay? So each of these is some kind of conditional variant divided by the unconditional variance is a number between 0 and 1. What's going on?
Sorry, it's okay. There was a little disaster here, almost happened, but everybody is alive. Yes.
Okay. So this would be the full variant decomposition, and these 1, 2, 3, 4, 5, 6, 7 terms, no? Okay, now it's manageable, but if these were 10 variables, it would be unmanageable. It would be 10 times 9 divided by 2, no? So 45. Now, so what we do is to compute ST1, for instance, which is simply S1 plus S12 plus S13 plus S123. And you do the same for T2 and T3. What is the shortcoming of this approach?
So it's ST2 and S.
So ST2 clearly is equal to S2 plus S3
So
plus S23
the indices 1 to 3
plus
are different
S12
variables,
plus S1, 2, 3. No? So you sum all the terms which contain the variable. No, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, and so on. But what is the shortcoming of this approach? If you can think of one.
Too many efforts to count. And the more variables
No.
you have, the higher.
Not because you don't need to know that. As I said, you can compute this in a single shot.
In a single shot, not
Yeah. No. You don't do this sum. This is what they are, but this is not the way you compute them.
The sum of the indices wouldn't reflect the overall variance decomposition because you have S1, 2, for example, twice, and S1 to 3 three times.
Okay, you have redundancy, no?
Yes.
So the sum, this cannot add up to 1, of course, because you are counting twice, no? Certain interaction. But as far as a single variable is concerned, this measure tells me everything that that particular variable is doing.
Right.
Okay, the full strength, either by itself or with his companions. Okay, his network. A person plus his network. Okay, so to go back there, you can express in plain English. I haven't said that to you, but for instance, the first order variance term, the one I wrote as V of E, no? Expressed in plain English is the fractional reduction in the variance of y, which I would achieve if I could fix xi. But you will ask me, but how do I know where to fix xi? In the middle, on one side, on the other side. So what I should say, more correctly, is the average reduction in the variance of y, which I would achieve if I could fix xi. So this is a measure of the strength of the variable. No? I can fix it on average, and then I get a reduction in the variance. So this is an important variable. In this way, you can explain in plain English to people what these are. No?
Can you say, or would it be already not precise, that then that percentage that you get is how much variance of the output is explained by that variable? Or?
Sí.
Okay.
With one caveat.
Yes.
Imagine that we compute instead the other sensitivity indices, which is instead this, E of V of Y X tilde I. This is the total sensitivity indices, and in plain English, this is the average, again, we had to use the word average, variance which would be left if all variable but xi could be fixed. No, also it gives the idea. Imagine I can fix everything but this variable. So what is left is really this variable. So again, if you ask me the same question, I still say yes. Also this is a variance contributed by the variable. No? And in principle, they should be the same. But they are the same only when you don't have interactions. Okay. When you don't have interaction, the variance which would be left by fixing everything but xi, and the variance which could be reduced by fixing xi, they are the same because they are no interaction. But when there are interaction, this one is larger.
Yes. So if you fix everything but xi, then you also take away the interaction effect. Kind of. You don't count it.
In a sense, yes. The way to understand this is the way in which you do the fixing, you know? The way in which you do the fixing, because in the second way you are fixing in a multidimensional space, so you are leaving the interaction active. In the first way you are not allowing this. And so in the first case, when you compute SI, you freeze the interaction, so you adopt a way of taking average which frees interaction. In the second way, you allow the interaction to act. So when in the process of taking the average, you still recover this interaction effect. But this is useful because so you can explain, in a sense, they are both fractional contribution to the total variance. Okay? But they are a bit different for this reason. Okay, so they can be expressed in plain English. And one property I haven't described is that you can apply the same variant decomposition formula. Imagine I put all my k variables in two groups, no? I split them in a group U and a group V. I don't know, some here, some there. But then I can write V equal V U plus V plus V U V. And this is the way in which Sobol first brought it. Okay, I was the one writing this one factor at the time, but Sobol wrote it in this way because he had in mind already the idea that if you could identify all the active variables and put them in a group, no, this would be very high, and this maybe also would be very high. Okay, so the idea that you can screen the variable and put all the important variables on one side and all the other in the other side, this would already mean that this is already close to 1. Okay, and if there are a lot of interaction, this one will be close to 1, the two of them, which means very few variants will be left to VV. Okay. Okay, so this idea, for instance, another important property, all these kind of variant decomposition formula only hold for independent variable, no? But if you have in your model a group of independent variable, a group of dependent variables, sorry, and you treat them as a set, you can still work with variant decomposition in the same way, provided you leave the group of variables that interact in a single set. Of course, when you do the process of moving, shifting, etc., you must apply to the set. So when I say, let's move the set of one step, you must change all the variables in that set of one step when you do the estimation procedure. Okay?
Because the sets are independent or not?
What I'm saying is put all the dependent into one group and then treat the group as if it were a single variable. Forget that the group is a group and treat it as a variable.
I don't remember who recommended this article, you or Art, maybe Art. There were some researchers who actually managed to do decomposition with dependent variables, second order effects, and then in the nominator there would be covariance, not just variance of the two, and then that value you can take negative effects, and then if you do approximation of second order effects with those things, you also can get negative values.
Yes, I'm a bit an enemy of these kind of things because, as you already said, it's, cranky. It's a bit cranky, no? More complicated to explain, and then there are also other way to do this variant decomposition in the case of variables which are not orthogonal. So this one I described is the one which is cleanest. No, there are even ways to when the input is not independent, you can have a sensitivity indices for the uncorrelated part and the sensitivity indices for the correlated part. It's come on, it becomes, you know, too much I mean, when you want to do a sensitivity analysis, you don't want to spend your lifetime on it. You know, you want to have a sensitivity analysis, get some result you can interpret, and then move on. Not to, eh?
Yeah, and publish.
Yeah, and publish. Yeah, exactly. Otherwise, you won't get your PhD. So I would. Another way I put it the following: nobody does a damn sensitivity analysis. Now, some people come and say, no, you have to do a sensitivity analysis and also have the correlated input and also decompose the variant. Come on, give me a break. So just do a sensitivity analysis which, you know, is decent and move on. Because considering the status of things where nobody does it in a quantitative way, I don't see much point in making it more bothersome. At least this is my philosophy. Huh?
Every paper that tackles dependent inputs, it has huge mathematics.
Yeah, they are complex. Yeah, but then imagine you communicating this, no? Yeah. Becomes even more complicated in terms of communication. So you already see that this is SI and TI can be used for factor fixing and factor prioritization, and then can give you the effective dimension. This we have seen, okay? So all this is more or less covered. If you really want to become a professional, do the exercise in the first chapter. It will take you maybe a couple of days, but then if you do the exercises, you are a master, a black belt in sensitivity analysis. One reason why, a proof that these methods are very good is that every person developing a new method, here we have Saman and Gupta, Saman Razavi and Hoshin Gupta, compare the performance of the new method against SI and TI because those are considered benchmarks. Okay? And you can use these indices to do a sensitivity analysis of a sensitivity analysis. Because sensitivity analysis may also depend upon parameters, no, or hyperparameters, you can do a sensitivity analysis varying those hyperparameters, no? And this is a way of doing a sensitivity analysis of a sensitivity analysis. Clearly, for instance, how many of you have heard about the Morris method? No, okay, that doesn't matter. But clearly, the method which needs extra hyperparameter is less good than a method which takes less hyperparameter, no? Okay. If the p-test could be used without having to choose a contingency level, it would be a more powerful test. Okay. Okay, this is a test when I said at the beginning. Now, if the function, if the output curve has long tail, maybe it's better not to use variant-based, but use moment-independent, which again are based on fixing a value and looking at what happened to the entire distribution of the output, and then do an average of this. It's a very similar philosophy of the sensitivity indices, okay? This is an article of Borgonovo.
From Bocconi.
Bocconi, yeah.
Emanuele Borgonovo.
Yeah, Emanuele. You know Emanuele?
No, just...
I was there a few days ago.
Really?
In Bocconi, yeah. I was listening to a group of crazy people calculating the GDP in the year 2300. And I kept saying, but you are crazy. And they didn't listen to me yet. Serious people, very serious people. Okay, I don't know why people do that, but... Okay, so don't use one factor at a time. This is what I was saying this morning, no? The idea that if you move into direction, you never go into the corners, and you leave out one quarter of the space. In 3 dimension, you leave out half of the space, but in 10 dimension, you leave out everything, practically, because the area of the sphere divided the area of the cube is 1/4 of 1%. And this is how the relation goes down, no? So really, when you are in 10 dimension and you do OAT, you are not doing anything. You are practically not moving. But this is due to the geometry, no? Because a cube in k dimension, all the volume is sucked up into the corners. Can you make a mental image of that? Imagine a hedgehog, no? A hedgehog, porcupino, how do you call it? This animal with a multidimensional hypercube is like this kind of animal. It has a lot of spikes, and all the volume goes into the spikes. So if you stay in the hypersphere, you stay in the core, and you miss all this cloud of spires. And this is why you have to explore the spikes, which is difficult, by the way, because you cannot go in all the. By definition, you can't even imagine that you go in all the spike at a certain level of dimensionality, and that's why even quasi-random number, when you go above 20 dimensions, they become as bad as anything else. When the space becomes really high dimensionality, no way of exploring gives you any guarantee because they simply are impossible space. No, there are too many corners to explore. Okay. And then you don't capture interaction. This is an example of interaction, no? Nice. So clearly, if you shake the ladder in the first side and then you shake them in the other side, the behavior is very much different. So if you want to test the scaffolding, you have to test the scaffolding in its entirety, not just one stair at a time. This example comes from this book of Savage Son.
And it's a very funny book.
Yeah, you read the book.
Yes.
Yeah, it's nice. It's a nice book.
Very humorous.
Very humorous. Yeah. It says if you have a pond where the average height of the water is 70 centimeters, you cannot drown in it. No, it's not true. Depends. If this is the average dimension, there can be a bump where you can drown easily, no? So this is why you should be very careful with the averages. Yeah. Okay, this is a paper where we studied. Also, it's better not to use method based on correlation or regression because they all need some kind of assumption on the form of the model, like, for instance, monotonicity. This is partial correlation coefficient or partial rank correlation coefficient. It's better not to use them. Those are very old papers where this was discussed, no? Where we compare the performance of this method on different test cases. Because they assume either linearity or monotonicity. And the point is that before exploring a model, you don't know whether the model is monotonic. Otherwise, if you knew everything about the model, you wouldn't do a sensitivity analysis in the first place. I'm a big enemy of Latin hypercube, though some people are fond of it, especially in America. But those who are fond of hypercube normally use, you know what is Latin hypercube sampling? It's a way of making a grid in the hyperspace and make sure that on every marginal you have 1 point per grid point. Okay? It's a way to try to put the point. It's a very mechanical way, if you wish, to try to have 1 point in each marginal. But you achieve this by working on the marginal, so it's not very mathematical. Mathematical is use discrepancy, no? Use quasi-random sequences which apply the same intuitive concept, but they apply it in k dimension, not in just one variable at a time. How do you make Latin hypercube better? You do many hypercubes, and then you choose the one with the best discrepancy properties, which
and hypercube is already suffers much more from dimensionality curse than the quasi-random, right?
Yes. Kucharenko has proven it because normally in Monte Carlo the convergence rate is 1 over the square root of n. But if you use quasi-random and the dimensionality is not 100, then you can go down as quickly as 1 over n, much more quickly, the convergence rate. And if you don't believe me, what you can do is to choose a function that you know well, of which you have the analytical solution. compute the integral of this function numerically, putting points into the hypercube, and do this calculation over and over using random or hypercube or quasi-random, and you compare the convergence rate. No? This you can do. Take you maybe one day of work, but if you do this, then you convince yourself that quasi-random goes much better, no?
Yeah.
But normally you should be below 20 dimension to see some good result.
10 minutes.
So this is a quasi-random sequence. This is Professor Sobol. The people who do, some of you are financial. You are financial people. This is for you. Oh, don't go away. Look, this is you. High frequency trading, you use quasi-random. Okay.
Yeah, you can use.
Yeah. So high frequency traders use this kind of sequences because they want to calculate very quickly, no? In a matter of microseconds, because the computer will decide the transaction, no? So imagine they have to do a VAR, value at risk calculation, which implies some kind of Monte Carlo integral over a portfolio, and they want to use quasi-random to get the result faster. Okay. I mean, these are the people who put the computer near to the stock exchange, because even the distance of the cables can affect the result, no? So they want to be closer as possible. They gain a few precious microseconds in
Kucherenko is there. The co-author is Kucherenko.
Kucherenko, yes.
Yes. Andrea, 10 minutes more. Is it okay?
Yeah.
Yeah.
And this is again one plot we made to show that, you see, quasi-random numbers go down much more. They start lower also, no?
Yeah.
Root mean square error with different design. Okay. A suggestion I give, if you are at the stage of model building, don't wait to have finished writing the model before doing some Monte Carlo, because, I mean, what does it cost to you that while you develop the model, every time you add one bit, rerun a small Monte Carlo, maybe, I don't know, 30, 40, 50, 100 runs. Because if you do this, you capture a lot of interesting things. You have a much more handle of what's going on with your model, no? Especially capturing errors, because the error always pop up when you use Monte Carlo, always. Because normally if you use a model always around the same nominal value, after a while it behaves. But if you move away, it will do strange things, and then you will discover something which should not be happening, and then you discover an error. Okay, it's useful. Ooh. So this is you can do a scientific career by doing this kind of papers, where you take a model which has been used deterministically, you run it Monte Carlo, and you show to the author that their estimates are not conservative. No, an easy way to make a paper in a sense. No, but you must
reply to you, and then it starts a correspondence.
No, luckily no, they were not allowed to reply. But they are welcome to write a paper in reply. You know.
That's what you mean.
No, they're not. No, they know that they are wrong. Yeah, clearly.
That's exactly what they do.
No. Well, they may, but as I say, if you have something to tell me, go to the journal and tell it on the journal. No?
Yeah.
Which is a bit arrogant, but sometimes the appropriate reply. I stand by what I computed. I publish it. You don't agree? Publish a paper when you show that I have made a mistake or something. So it's yeah. You don't make many friends, maybe, but. Okay. And this is and Arnold is really, Arnold Pui is really now hammering this in. The shark, yeah, is killing all these ideologists. And then he can say, listen guys, you are doing really a bad service to mankind because you are underplaying the risk from irrigation to food production. No? So it's nice that Arnold does this work. And these are, all these the goals. Okay.
Andrea,
Yeah.
if there is a concluding remark.
A concluding remark. This I described already. What time do we stop? At 4? You were planning to stop at 4?
We can start 4:15, so a few minutes more.
Few minutes more. Let me repeat what I said today because this is nice. No, okay, this we can. No. Let's see, it's here. No, this is not. Okay, this is to show that you can sample many things. No.
Last one was good.
This was about sampling all the value by changing all the variable to give all the variable the same range of variation, which I think is truly crazy because this is never the case.
Like plus minus 50.
Yeah. This is totally meaningless. They have done this in this report. I think they are really amateur. Should never be done. I mean, that's why. If you are so ignorant about your parameters that you believe that they are all uncertain by 10%, it's not even worth doing an uncertainty analysis because you don't know anything.
You can claim that you did it at least.
Eh?
That's the point. You can claim that you did it at least. And I guess.
Yeah,
I
but
think that it's done in some cases just.
But it's
somebody asking for it and you just do it, whatever.
exactly. This is perfunctory. I do it, so.
Yeah.
But I didn't put any concentration into it because to do a good uncertainty analysis, you have to concentrate on how uncertain can this be, how uncertain can that be. No, and this is the most important part of the analysis because if you get those ranges wrong, the analysis is useless. Okay, I stop here. So maybe we can have.
Thank you, Andrea.
Okay, thank you.